can say LG fault is nothing but SLG fault, single line to ground fault. So whenever we take this single line to ground fault, there will be a rise in a voltage in other healthy phases. So let me take three phases R by B. So now I am assuming that one of the phase is connected to the ground, one line is having a fault. So now because of this single line to ground fault, what happened, in other two phases there will be increase in the voltage, there will be increase in the voltage or rise in the voltage is going to happen because of a SLG fault in one phase, that is because of single line to ground fault. So usually with a solid grounded system, the increase in the voltage will be less than the line to line voltage. If this three phase supply is connected to some generator, or this generator is connected with a solid grounding, okay, if I am connecting with a solid grounding, then the increase in the voltage will be less compared to line fault. If I take a line to line fault, double line fault we can say, so compared to that the fault will be less in a solid grounded system. So where in this case where X0 will be, the ratio of X0 into X1 will be less than or equal to 3 per unit, and R0 and X1 will be less than or equal to 1 per unit. So where R0 and X0 are a zero sequence resistance and reactance of your transmission line, and X1 is a positive sequence reactance of a system. Once again this regarding positive sequence, negative sequence, so that we represent as a 1 as a positive and sometimes 2 as a negative, and 0 sequence will be represented as a 0 only. So all these parameters related to this fault, symmetrical fault, unsymmetrical fault, so in detail we will be studying in the next semester in a PSA 1 subject over there. So this rise in the voltage in healthy phases will not usually exceed usually 1.4 per unit because of single line to ground fault. As I mentioned, there will be a rise in the voltage in a healthy phases that will not exceed almost all say 1.4 per unit, it will be below that. So the next one effect is saturation effect. So whenever we have a voltage above the rated value is applied for a transformer, we have a power transformer in a transmission line, we make use of a power transformer, suppose say it is rated for 440 kV, and let us assume the other side is 220 kV, it is a step down transformer. So if this is the case in terms of kV, okay, when you apply the voltage for the transformer above this rated voltage, so instead of 440 I may give 500 kV or 600 kV, okay, I am applying with a higher voltage. So now what happens, their magnetizing current, if you take a circuit, if you remember your no load circuit is called as a magnetizing circuit, so where R0 and X0 will be there, right, R0, X0. So the current which is flowing here will be your magnetizing current. So this magnetizing current, that is a no load current, will increase rapidly whenever you give the voltage above the rated voltage for any transformer, that is a power transformer, okay. So this magnetizing current will increase rapidly and maybe about full rated current of 50% over voltage. So this is maybe 50% of the over voltage current. So just imagine whenever we have a over voltage, so we say that if it is doubling the voltage, that will affect the system. Now the current is increasing 50% of the over voltage because of I am giving a above the rated voltage. Because of that there will be a huge amount of magnetizing current will be increased. This magnetizing current are not sinusoidal in nature, they won't be pure sine wave, they may have some disturbance within the sine waves, it won't be a pure sine wave, and we may have some peaks also which you can see here. So within a sine wave we may have peaks like this, so which is not a pure sine wave, we may have more number of peak waves, or we say peaky waveform. So usually there will be a third and seventh harmonics content may be present within these waveforms. So whenever there is, we say that it's not a pure sinusoidal waveform, obviously we say that there is something harmonics in the system. So that harmonic usually will be of third harmonic or fifth harmonic or seventh harmonic within the system. So this third harmonic, fifth harmonic, seventh harmonic will be having a percentage. Third harmonic will be of 65% will be present in the system, and in the fifth harmonic will be present 35%, and the seventh harmonic will be present 25%. So because of this harmonics only, there will be a non-sinusoidal waveform or a peak waveform will be present when there is a magnetizing current is rising in the transformer. So this third harmonic and multiple harmonics, as well as zero sequence impedance value and effective, all this can be suppressed if the transformers are connected in a delta fashion. If your windings of your transformers are connected in a delta, I can suppress your third harmonic and also some multiple harmonics, zero sequence impedance value, right? Other which are the parameters will be affecting the transformer, that can be easily reduced if your transformers are connected in a delta fashion. But the shunt connected capacitors and the line capacitors can form a resonance circuit. We may give a compensation where we say the capacitors will be connected in parallel to your transmission line there near to your transformers, as well as if your line capacitance, which will create a resonance circuit which will cause once again the third harmonics overvoltage. So this also will give rise to a third harmonics overvoltage. When this overvoltage will get adds, once again the voltage rise will happen within a line significantly. Already there was a overvoltage, because of adding some compensation also will lead to a overvoltage within the system. So this is called as a because of a saturation effect, where the transformer magnetizing current is increasing in a transmission line. So these are few reasons related to the overvoltage with respect to the power frequency.